Let's see if we can go step by step to at least get started on this week 5-6 assignment for strain and second order response. So this is the first question that we had. The target here was to estimate the parameters K and C that go into a second order equation like this in order to predict a behavior that'll be similar to what we measured in the lab. So as a starting point, the question suggests we could try setting K and C equal to 2007 and see what comes out as a starting point. So I'm going to start with my own raw data, and built right into the assignment was the code necessary to import that data. So if I run that code, it loads up the data and it plots out the results that I got. Now this red one looks like it was bouncing up and down a little crazy. I think that was too small a weight, dropped from too high above the bucket to get some good results from. But that blue one, that looks a little more reasonable. So let's have a look at the blue stuff. That's test number 1. So I'm going to just plot the first test and not plot anything else. So let's plot that out and see what we find. Well, it looks like the initial mass was around 3.3 kilos. So let's set that M0 to 3.3. And it looks like the middle of the oscillations out here after a while was about 3.5 or 3.45, something like that. And that the time at which things really started happening was at time t about 0.06 seconds here. So we'll call that the starting time. And so what I'd like to do is I'd like to get my model, this differential equation up here, I'd like to get that model to give me a response that looks at least something like that graph. So to get that, I know I'm going to start with a step function. So I went from 3.3 up to 3.45 kilos on the load cell, and I got some oscillations like that, which were damping out over time. So let's start with the stuff that we had from our example about extracting second order models. And first off, I'm going to take n equal to 100,000, just like I did before. And then I know that my data goes on for about 1.5 seconds. So I'm going to set T max equal to 1.5. And then I'm going to get a time base that's a linear space that goes from 0 up to T max, so 0 to 1.5 seconds. And it's divided into n different values here. So that's 100,000 different steps. So that's the time. And the time step, dt, will be equal to, well, t, whoops, not capital T, lowercase t max divided by n. So that's how long a time there is between each time step. And then I'm going to make my y value, my applied load, my input, be a copy of the time, just to make sure that it's the same size. So I can run that, and it runs okay. That's good. Now, next I'd like to make an approximation of what's going on here. So let's try plotting that out. I'm going to copy this plot stuff again. And I'll add that in there. So I've still got the same graph, but now I'm going to also plot on it the values against my time base t of my input value y. Well, that's not very interesting. All I've done is made a copy of y so far. So I need to actually fill in what I think y is going to be. I think it's going to start out at 3.3, and then it's going to jump up to 3.45, and then it's going to continue on flat. That's my step function that I think is my input when I dropped stuff into the bucket. So after we make a copy, then I'm going to go for I in a range from 0 up to n. And if the time at value I is less than, well, it should be less than 0.06. And up here we said the start time was going to be 0.06. So if it's less than 0.06, then y should be equal to m0. And I need a colon there for the if statement. Otherwise, else y at I should be equal to m1. So I'm approximating what's going on as a step function. Let's see what happens. So, whoops, didn't I run that one? There we go. So it starts off at 3.3, it goes up to 3.45. That looks like it's matching up at both ends. So now let's try running the model and see what comes out. So we'll go over to this example code that we had before, and I'm going to copy this stuff. And I'll paste it all in, and then I'll see where I go with it. So paste it all in. Well, we already said that n was going to be equal to 100,000. So we don't need n, and we already defined Tmax, and we already defined that space. We already made that copy of y, so I don't need that part of the code. And we already assigned the values of y to be the step function, so I don't need that part of the code. I'm going to need this part because it sets the initial conditions. It makes sure that the measured y0 is the same as the actual input y0, so it's in equilibrium. And the two derivatives are both equal to 0 at time t0. And we already calculated dt, so we don't need to calculate that again. I'm starting at 2000 and at 7 because that was the numbers that I had up there as an example. And now here's the part where it does the calculation. So it's calculating the new value for the model equal to the old value for the model, the value that it had at time 0, plus the derivative times dt. So that's just an Euler advance. It's going from the new value is the old value plus the rate of change times delta t. And the same thing, we can advance the first derivative based on the old value of the first derivative and the second derivative times delta t. And the second derivative, that's the one that's actually got all of that information in it from the differential equation. So k times y minus ym and c times the derivative, the velocity. So that should be the part that does all of my calculations. Now I'm going to get rid of this just so that we're careful here. And let's run that. Well, the calculation ran, but we need to plot some stuff. So let's plot the input that we used, and that was that y value that we'd calculated up here. So we'd said it was going to be equal to M0 before the jump here, and M1 after the jump, and we got that orange stuff. So let's plot the time and plot y against it. And then let's plot our calculated values from our model. So that's the actual input y. Here's our model's predicted y. And if I plot those, I get something that starts at 3.3 and winds up at 3.45. After the step function, it oscillates up and down like that. That looks a lot like that graph, that blue stuff. It's damping out faster than the blue stuff, but otherwise it's got a lot in common. So let's put the blue stuff on there as well. It was this one. So I'll go down here and I'll put that blue stuff on there just so that we can compare them. Oh, and now we see actually the measured data, the stuff we got from our measurements, was oscillating up and down quite a bit more. So if I wanted to make the orange one oscillate up and down at about the same magnitude, it looks like I'd need a bigger step. It's zeroing into about the right place at the end, but at the beginning, I think maybe what happened was I dropped the weight, and the result was it added a lot more force than just its mass to get started with, and that got me a big bounce to start with, and then it damped out somewhat. So let's make the bounce bigger. So let's go up here and try, what did I do? I was way back up here. Let's make that 2 instead of 3.3, just to get a bigger bounce. Doesn't change any of that, but now when we go and do our calculation, okay, now the bounce is about the right size, but it's damping out too fast. So I'm going to decrease the damping coefficient. Let's make it about 3. It's not damping, it's doing about right there. It doesn't look too bad. Maybe still a little fast. Maybe call it 2. So that looks like it's got about the right amount of damping on it. But the frequency doesn't match up. If you'll notice, the period from there to there is longer, so it's going a little too slowly in the oscillations here. So let's try to speed it up a little bit. Well, the stiffer it is, the speedier it'll be. So let's try going to 3,000. Now, at this point, that corresponds to that trough. That corresponds to that trough. That corresponds to that trough. It looks like through most of the region in the middle here, I'm getting about the right frequency. So I've got about the right level of damping. I've got about the right frequency. I think I've got a reasonable estimate for those parameters. I maybe could do better, and you could try to do better, but that's not a terrible model. So I started off by not knowing what these parameters were, and now I've got a pretty good idea about what they are for the system that I'm looking at. And I got it from this drop test, even though, as it turns out, this drop test wasn't really quite exactly a step function, but it's still got some of the same characteristics. So I'm reasonably confident that I'm in the right kind of neighborhood with these parameters. Now, what was the mass that went along with these parameters? Well, it was this final mass value of 3.45. So that goes along with about 3.45. Suppose I was interested in how it would behave with a different mass? Well, remember that these coefficients are inversely proportional to mass. So the lower the mass, the larger the coefficient is going to be. So down here with the chicken, it's telling me I should assume that I've got a 1 kilogram total mass. So if I only had 1 kilogram of mass, then what would my coefficients be? Well, 1 kilogram divided by 3.45 kilograms, that would be a ratio of the two. And it's a mass ratio, and it's inversely proportional to mass. So as mass goes down, K and C are both going to go up. So let's try calculating that. I've got R. Now let's let K equal to K slash R, whoops, lowercase r, and C equal to C slash R. And now let's print the new values of K and C. So I go from, what did I have? I had about 3,000 and a C value of 2, and I went up to a little over 10,000 and a C value of almost 7. So that's increased a fair bit. Now, suppose I wanted to use a different forcing function here. In this one, this y is what I was using as my forcing function. So let's get rid of our other plots here, particularly this data plot. And so that was the forcing function I was using. It was going from 2 up to 3.45, and it was doing it as a step function. Now that's the simplest one we could have if we suddenly increase the mass. But with this chicken running across, what we've got is a forcing function. This load that's applied to the load cell goes from 0 up to about 5, down to about 0, up and down and up and down and up and down and so on. So we need to somehow come up with a function for that. So there's our y, and it's checking in the range so that when it's down here, it's equal to 0. So if I set my y equal to that instead of equal to the step function, then I could go back up here and run this with a different y now. And I'll use the different k and c as well that we've got before. So if I run that, well, now there's the forcing function that I've got. It's different from what I had before. And now let's plot out what I get as the output of the model. Ooh, something weird is going on here. So it's quite bouncy up and down if I use those values for k. That's kind of frightening almost. So what do you think is going on here? I'm not sure, but I think this chicken is making that force platform bounce up and down. So you'll probably get different values for your calculations based on your particular data and the coefficients that you have here, what you figure out for yours. But I expect that when you put that different forcing function on there, you're going to see some fairly wild oscillations. But let's try it a little differently and see what happens if we make this system much stiffer. it's much stiffer. Oh, we're following that forcing function much more closely, even though we've got some oscillations in here. So taking that approach there, you can first figure out what's likely to happen in this case with this forcing function. You can determine what these constant coefficients ought to be by making it match up to that forcing function. And then you can go and calculate some values down here for a different forcing function. So try that out yourself and see what you get. It won't be exactly what I got, but it'll be the same kind of process.